All right, so we continue to give these examples. So let's talk about the centrifugal force concept. So I said that what you experience inside a bus can be explained by this fictitious, can be formally explained by adding this fictitious force. So in any case, so what happens is that whenever the bus accelerates, it appears that on you, there's a fictitious force in the opposite direction to that acceleration. Okay, so if it accelerates forward, the fictitious force on you is backward. If it slows down, if it brakes in the forward direction, so that means velocity is in the forward direction. If it brakes, then the acceleration is backward. In that case, you are pushed forward. And finally, when the bus takes a turn, let's say that it's taking a left turn, in that case, the acceleration of the bus is in the leftward direction towards the center. Okay, so in that case, the fictitious force on you is in the outward direction. Okay, so in this special case, it's also called centrifugal force. Okay. However, again, let's just remember that this is basically inertia. So the fact that inside the bus, the bus was moving with that particular velocity, and inside the bus, you are also moving with the same velocity, right? Let me show it like that. Your velocity will be exactly the same as the bus's velocity, but because of inertia, because there are no forces acting on you in the horizontal direction, you tend to move in the forward direction, but somehow the wall of the right wall of the bus, this wall in here, is taking a left turn, right? So as a result, at some point, you are going to hit to the right wall of the bus, because somehow you're going to meet somewhere, right? So you're essentially doing this motion where, since there are no net forces on you in the horizontal direction, you're just moving with the constant velocity, but the bus was not moving with that constant velocity. So as a result, you eventually meet. But it appears that if you just take the bus's reference frame, so in that case, everything else around you will be accelerating. The bus is at rest. So in that reference frame, it appears that as if there is a fictitious force acting on you in the outward direction. Okay. So in any case, so that's called the centrifugal force. All right, that's basically because you're solving the problem in a different reference frame. So as a result, think about these kind of problems, right? You just swirl something, some object, for example, on top of your head, for example. So that's the, all right, that's the way that it rotates. All right, let's just do it like that. Okay. So this is a typical circular motion problem. When people solve these kind of problems, they add these, like for example, the tension force on it, and somehow they also add this mv squared over r. So when you're solving it like that, I believe that this is just an artifact of this Dersane system. Well, I don't know. In any case, so if you are solving the problem like that, in that case, what you are essentially doing is that you're taking this object as your reference frame. And actually, it means that you're also using this rotating reference frame. So it's not just an accelerated reference frame, it's also rotating as well, but that's a separate issue. And within that reference frame, the object is at rest. And then you're saying that, well, there are these two forces acting on it, and the object is at rest. And so therefore, you then solve for the value of the tension force. Okay, so in this kind of a solution, let's say in this particular type of solution, that's what you do. Okay, so first you take the object as your reference frame. Okay. 2, object is at rest. So that means its acceleration is 0. So the 0 acceleration. Okay. So as a result, together with the fictitious force, so there are these real forces on it, and then this mv squared over r. So that's the fictitious force. And this is the real forces. Together with this, the net force is 0. Net force, therefore, is equal to 0. And then you say that T is equal to mv squared over r. Okay. You solve the problem like that. Okay. So as a result, this kind of a solution involves passing to a different reference frame and then by using this reference frame to solve the problem. However, the problem is that, I mean, this problem is not difficult at all in the ordinary reference frame. So in the ordinary reference frame, this is the picture that we have. So there is a tension force acting on it. So that's the only force acting on it. And as a result of that, it has an acceleration. Right? So that's also given as v squared over r. So as a result, what you do is basically you write down net force is equal to mass times acceleration equation. So the tension is equal to mv squared over r. Right? Nothing complicated in here. So as a result, passing to a different reference frame is not justified for these kind of simple problems. Okay? So if you are doing this because somehow in high school you have learned this method, then just forget about it. Okay. I mean, it doesn't give you anything, but there are some certain particular problems where you actually gain some kind of a better understanding of some certain things. Okay. So I'll talk about some of these. I don't know if you have any questions in here. I mean, in the exam, on online exams, probably that's not an issue, but in the exams, we actually see these kind of solutions, and usually we take off points from these kind of solutions. So if you just write this thing down without mentioning that you're using this accelerated reference frame, this is a mistake, okay? Because normally, if you don't mention anything about it, we assume that we are using inertial reference frames to describe what's going on in there. So if you don't mention this and still draw these kind of things, that's a mistake. That would also be a mistake in here. So if you just want to solve this problem and find the acceleration, if you remember that problem and find the acceleration in here. So if you just do this in here, that also would be a mistake, right? I mean, formally it is okay, so you're basically taking the block as your reference frame. So the block is at rest. So that's the fictitious force. That's the force. So from here, you can find the acceleration of the block in the original reference frame. But we never do this kind of a thing, right? I mean, to solve that problem, we can just use this ordinary inertial reference frame, and we never use this kind of an accelerated reference frame here. So let's say that this takes the block as the reference frame. There's no advantage of passing to this accelerated reference frame. Okay, just keep this in mind. So I'll just show some problems. Okay. So let's start with this. Bus accelerates. Perhaps we can talk about jerking here. Accelerate to the right with acceleration. AB is equal to 5 meters per second squared. If the hanging mass is not swinging, find theta. All right, let me just draw it like that, all right? Probably I should have drawn the picture first, but okay. In any case, so there's a bus in here. Bus is accelerating. So that's the picture in here. So somebody hanged something to the ceiling. But the bus is accelerating with a constant rate, right? It's not just speeding up and then moving with constant velocity or anything like that. It somehow maintains this acceleration for a very long time. So it's just an unphysical situation, but let's suppose that this is the case, okay? So you just hang something, but I mean, normally it would swing, but it somehow remains at rest relative to the bus with that angle, right? And the question is, what's that angle? What's that angle theta? We can solve that problem in this ordinary inertial reference frame. No problem with this, with an accelerated reference frame. So let me just compare these two. Let's say this is the inertial reference frame. So that's bus's reference frame. Okay. In the inertial reference frame, we just draw the free body diagram like that. So there's a tension force like this. This angle is theta. There is a weight force acting on it. And as a result of that, this object has an acceleration which is equal to the acceleration of the bus. In the bus's reference frame, things like that, let's say the tension is like this, all right? The weight force is like that. And there's a fictitious force in here. So let's say fictitious force. So that's mass times the acceleration of the bus again. So by AB, I mean this magnitude in here. So it's 5 meters per second squared. So fictitious force is therefore towards left, and it has this magnitude in here. Okay, and let me just add in here that there is no acceleration. Okay, so sum of the forces equal to 0 in here. So in this frame, we are going to say that T sine theta is equal to mass times the acceleration, and T cosine theta minus mg would be equal to 0. Okay. And here we are going to say that, well, T sine theta minus MAB is equal to 0, and T cosine theta minus mg is equal to 0. Okay, so in one case, this term appears on the mass times acceleration side. I mean, I'm writing basically F equals ma in here, right? The forces are on the left-hand side, accelerations are on the right-hand side. In one case, this term appears on the right. In the other case, it appears on the left. Okay, so the equations are the same. Again, there is no particular reason why I should solve this in the bus's reference frame. I could have solved it in the inertial reference frame as well. No problem at all. Okay. All right, but in any case, so from here we say that, well, T sine theta is equal to MAB and T cosine theta is equal to MG. So the ratio is, well, I just need to divide these two. So the tangent theta is equal to AB divided by the gravity. So in that case, that's equal to 1/2. So theta then is the arctangent 1/2. Whatever it is, I'm not really interested in the value, numerical value in degrees for what that angle is, right? So we know what the angle is. We can compute what the angle is by using this formula. Okay, so that's the answer. So what's the advantage of the accelerated reference frame? Okay, so the important point in here is that this fictitious force appears like gravity, actually, gravitational force. So just keep in mind that the gravitational force acting on an object is always proportional to the mass of the object. The fictitious force is also like that. So that's an important point to keep in mind. So note fictitious force is, let's say, quite like the gravitational force. Okay, so basically the fictitious force is in the form of mass of the object and the acceleration of the reference frame. So I'm just going to come back to this. So this is the mass of object, and that's AB is the acceleration of the reference frame. Acceleration of reference frame again. So again, just keep in mind that it's not the acceleration of the object. So it has nothing to do with the object. Okay. So in any case, so it appears that this actually looks like gravity. So as a result, I can basically think of this as a fictitious gravity. Okay. So we can think of this as a fictitious gravity. Okay, so as a result, the formula in that case for the fictitious gravity is minus the acceleration of the reference frame. Okay, if we just think of it like that, in that case, things are simpler. So in that case, right, inside the bus, let's say there are two gravities in a way, right? Two gravities, okay? So one is the real gravity. So that's the real one. And the other one is the fictitious gravity. So that's the fictitious gravity, okay? So we know their magnitudes, but in any case, at the end, I can then talk about this total gravity in here. All right, so that's the total gravity. So this G tot is basically the sum of these two gravities. One is the real one, and the other one is the fictitious one. Okay, so that's the total gravity. And so as a result, I can think of things in terms of this total gravity. So I can easily see that, for example, in that picture, so that angle theta is basically arctangent, arctangent the magnitude of the fictitious gravity divided by the real gravity. So therefore, this is arctangent AB over G. So that's arctangent 1/2, right? And the magnitude of the total gravity is, in that case, well, I mean, this is just geometry, right? That part is quite easy to deal with. So as a result, what happens in here is that within the bus, there is gravity, but it's a gravity along this direction. That's the total gravity, okay? Of course, again, this is imagined. I mean, part of that gravity is imagined, but if there were some real gravity inside the bus directed like that with a magnitude given by this, in that case, everything happening within the box can be explained in the same way, right? So as a result, I'm thinking of an equivalent physical situation where the gravity is like that, and then describe everything by using this picture. So I know that if I have this kind of a situation, and if I hang something in here, some object with a string, I know that this object is going to hang with the same angle. So that angle would be the same as because every hanging mass will be pointing in the direction of the gravity there. And so as a result, I could answer this problem like that. Real gravity bends space-time, but fictitious doesn't. I would say it like this. I mean, this is the principle of equivalence of Einstein. I mean, the idea in here is that the thing that we can, the next step that we can go from here is that perhaps we say the real gravity is perhaps is fictitious. Okay. I mean, that's the next idea. Okay. I mean, let's just say it like this. So as a result, this is essentially the essential idea of Einstein's general theory of relativity. So he explains gravity like that. He tries to explain it, but there are some difficult issues in there. And so as a result, the theory has to be mathematically difficult. So when we come to gravity, I'm going to come back to this, and we will cover this thing. We will go over this thing again. So at that point, we will try to explain the real gravity in some alternative way. Excuse me? Gravity can be greater or less than Earth's gravity. Can be less than, yes. Yeah, because we are adding this fictitious one, and fictitious one can be in any magnitude and in any direction, depending on the acceleration of the reference frame. Do we call forces as fictitious where forces are on different dimensions? I don't know what you mean by dimensions. So fictitious force in here is that I'm using a reference frame, and which is accelerated. So I'm basically correcting the fact that I'm using an accelerated reference frame. I shouldn't use an accelerated reference frame. I shouldn't use such frames, but I'm using it because somehow I'm stuck inside that bus and I have to view everything from that bus's point of view. So therefore, I have to use I have to add this imaginary force in here. Okay, let's not talk about gravity and the other issues. So let's just talk about this. I had some, sorry about this. I had some polls, if I can find. Yeah. Okay, so that's a good problem, but first let me draw the picture in here. Okay, so in any case, it's the same bus. Okay, it is accelerating towards the right. So let's say that this is 5 meters per second squared. Sorry, I did it in the other way. Yeah, sorry about that. Forget about this. Right. So the velocity is like that. Sorry about this. Let me try to explain this. Okay. We are still in the same situation. Okay. It is this situation in here. Which one? Yeah, forget about this. All right. The bus is accelerating towards right. All right. Let's just say it like this. And we are inside the bus. So inside the bus, it appears that the real gravity, the total gravity is basically at an angle. So as a result, by using this, I can also explain my behavior. So if I basically stand within the bus like that, with this position, right? Because the total gravity is along that direction. Total gravity is along that direction. I mean, if I actually stand upright relative to the direction of that gravity, then I will stay upright. But that person in here, probably that's a stupid person. He tries to stay upright. He tries to stay perpendicular to the floor of the bus, but somehow the gravity is along that direction, right? So I don't know how to do this again. Perhaps we can actually think about this better if we just rotate this thing. In any case, so the gravity is, or the downward direction is like that. That person is basically leaning in some direction. So as a result, gravity is going to basically pull that person off, and then that person is going to fall down. right? Again, I mean, this is the picture in here. So if there's a bus which is accelerating in the forward direction, then if I am leaning like that, I won't fall, but that person who refuses to lean in the forward direction will basically fall back. Is this reasonable? And also, I mean, if I have a pendulum or something like that, it's some kind of a swinging mass, that swinging thing will actually be leaning like that, okay? So everything will be leaning parallel to the gravity. Okay, so the next question is this. So what happens if we have a brake? So we are inside a car or a bus. And yeah, let's say that it's a bus, okay? So suppose that the velocity of the bus is along that direction, but it brakes, which means that the acceleration is in the backward direction. Okay, let me show you the pole. So there's a balloon which is tied to one of the chairs of the bus. When the bus brakes, does the balloon go forward or backward, right? So there's a chair in here. A balloon is tied in here, right? So the question is, it's a flying balloon, all right? Yeah, that's it's a flying balloon. There's some kind of helium filled, right? So the question is whether it goes backward or forward. Okay, this is a confusing question. All right, let me end the poll because we get the essential idea. I'm going to share the results. A lot of people said forward, but let's just discuss it like this. I mean, sorry about this. So the velocity is towards left and it brakes, meaning that the acceleration is in the backward direction. So in this case, because of our analysis, the fictitious gravity is in the forward direction, right? It's basically opposite to the direction of the acceleration of the frame. So the real gravity is like that. So that's the real one. So therefore, the total gravity is in this direction. So that's the total. Okay. And because of that, I don't know, we are going to fall in the forward direction. And as a result, we try to orient ourselves parallel to the total gravity. So I know that the hanging mass is going to go forward because of this fictitious gravity in here. And the question is, why doesn't the balloon do the same? Shouldn't it go backward? Because it basically tends to be oriented parallel to the gravity, because I mean, that's basically what happens in the usual gravity. If I hang something to the ceiling, it will be pointing parallel to the gravity. A flying balloon also will be anti-parallel to the gravity, right? So as a result, within this bus, for example, the total gravity is along that direction. So that's the direction of the total gravity. And I know that this hanging object is going to become parallel to the direction of the gravity. And the question is, why shouldn't the balloon be doing the same thing? So shouldn't I expect it to go backward? Can I open this, or should I actually leave that to you? Sorry about that. The balloon is already going backwards, right? I mean, there are two competing things in here. One is the inertia thing. So the balloon, in that case, has some kind of an inertia, just like us. So as a result, it will tend to go forward. The other thing is the gravity thing. So if the gravity is actually along that direction, in that case, the balloon tends to go backward, right? So there are these two competing issues. So one of them is a little bit more dominant than the other one. All right, all right, thank you very much, Bashar, Deniz, Sevinç. Right, I mean, let's just remember how the balloon is actually, why the balloon is going, is flying. This is actually Archimedes, buoyant force, Archimedes law. Yeah, what happens is that I mean, normally the balloon should be also attracted by the gravity. Normally, if there were no air, but I know that there's air, so we know that air has pressure difference. So there is high pressure region at low places and low pressure above, right? So because of that, there's some kind of a net force by, let's say this is the buoyant force, F buoy. So that's the net force by air molecules. So what happens is that the air molecules apply a much bigger force in the downside of the balloon than the ones on the upside. And because of that pressure difference, there's a net force on the balloon, which pushes it upward. And since that force is bigger than the gravitational weight of the balloon, the net force is in the upward direction. So as a result, we have this kind of an issue. So that's the why that the flying balloons are pointing in the upward direction. So in that case too, the air is going to be, because of inertia, the air is going to be rushed in the forward direction. So as a result, because of that, the front part of the bus is going to have high pressure. And so as a result, the backside is going to have low pressure. In any case, I mean, there will be some kind of a pressure distribution, which is basically consistent with the direction of that gravity in here, right? Because of that, the net buoyant force on the balloon will be basically in that direction. So as a result, this is going to go back. Okay, so let me just say it like this: balloon goes backward because of buoyant force of air molecules. It appears that this is dominant, but I actually didn't see any YouTube video that people have actually tested this. I don't know. I mean, if you are riding buses and the bus keeps braking, perhaps you can test this. I don't know. It's just an idea. I mean, it's not something which is quite easy to test because I mean, to have these kind of significant differences, we should have like very large accelerations. But I don't know. I mean, perhaps it might be some kind of a noticeable effect, right? So when hanging things actually go forward, you expect the balloons go backwards, so that they actually still try to keep parallel to each other. Okay. Hacı Yatmaz is going to go forward, right? Because is it? That's an interesting question. So I think there's also this initial motion as well. There will be some kind of an initial motion, and then when everything settles, it's going to go back, perhaps. There are these kind of situations. Yeah, let's just look at this video. I don't know if... yeah, I'll look at it, all right? So right now, let's just continue with this. Yeah, we don't have much time. Sorry about that. Okay, so tomorrow we are going to continue with this, but some other problems like this one. So I know that you're a balloon in a car. So that's nice. Thank you very much, then. Yeah, I'm going to solve this problem. So we have an elevator. Okay, so we have an elevator in here. Elevator accelerates. And we are going to solve this problem of computing the accelerations of these. So in that case, too, the solution within the accelerated reference frame is easier. So all you need to do is to basically change the value of the gravity to the real gravity, sorry, the total gravity. So instead of using the real gravity, you have to use the real plus the fictitious gravity. So as a result, once you do that, then the problem becomes the simple problem, right? Simple problem of that we have already solved before. It's just that the gravity has a bigger value now. Okay. So as a result, we are going to solve this problem, and to illustrate, I'm going to solve this problem both in the accelerated reference frame and in an inertial reference frame, and then we are going to compare these two. Okay, so tomorrow we are going to solve these. So I think I'm going to mention a few other things as well, okay? But I just forgot these right now. Okay, so let's stop this. Let's continue tomorrow.